The impression it's not very warm here. So if you feel like you need to warm up, feel free to stand up and do some exercises. Okay? I'm running around, but you're sitting. I have a question of this gentleman here. I forget your name. Charlois. Yes. Charlois is a doctoral student at IMEC. Yes. And on Friday mornings you have a course which you have to follow, which is very expensive. Well, and if you don't follow it, you will be fired. Yes. So this is very serious. So the question then is, should we now do all our lectures in the evening?
What time exactly?
Because you like
it's more important than our hours. I mean, it's not that we're going to lie if we have a lesson. It's going to be 1 on the 7 p.m. It's okay.
Yeah, but I have the impression there's a little bit less attendance here in the evening. It's kind of cozy in the evening. If you would have a little wood fire, it would be even better, you know. some glue line and things, yeah, that would be great. So for me, it's fine. But
lectures, it's fine for you, right?
For me?
You can skip the lectures.
If you skip the lectures?
Yes, for this lecture.
Yeah, please skip lectures. As I said, if I have an empty classroom, I don't have to teach. So if all of you stay away, shall we agree on this? Shall we make a deal? You don't come to the lectures and I don't give them. We just do the exam. Yeah, you just do the exam. You do brilliantly on the exam. And this is great. So no, yes, I'm happy to teach this class as well. But everybody's free. You're not fired. I won't fire you. Right? I don't have the power to fire you if you don't come, and I won't fail you if you don't come. Because I have a terrible memory, so I don't even know if you were in the lectures.
I want to be in the lectures.
You want to be in the lectures. This is a.
Of course.
So, but you don't want it bad enough to get fired, I think, eh? This is a, okay. No, don't say you like this lecture that much. This is too much of a compliment, I have to say. So, yeah, I'll ask the question, but I'm not sure if we just want the majority or 2/3 majority or something to decide. This is, of course, also on decision making. I don't know how the statistics would work on this. So, for this population, who prefers evening, who prefers morning? Evening?
Evening, which day?
Could be this day or Thursday or Saturday evening if you like. It's kind of a warm-up for your Saturday evening. So, shall I put, I don't know how to put the question. I could do this by a doodle or something, right? I could send all of you a doodle link and then you say evening or morning. And then the majority decides. Yeah? We just have the majority decide, or do we need more than a majority to go from morning to evening? Because I have to, then I have to give work to the secretary as well to find rooms and things, which is not so difficult in the evening, to be honest. I mean, it seems that nobody else wants to do this in the evening. So I'll organize a group. Yeah, it's an interesting experiment. Thank you. So we'll see how that works. But I think also for the exercise sessions, I'm not sure if the assistants want to give it in the evening as well, so I have to check with them. Exercise. Now we have 2 exercise sessions. The first one would be next Friday morning. Exercise session. So we need to see how that works out. So, okay. I'll organize a Google. But then you have to reply quickly. So let's say you have to reply by Monday evening. And the people who have replied by Monday evening, then decide where we go. Okay? Wow, this is democracy. It's very exciting. Okay. So let's, and if it's still the morning, then you still have to make a choice if you want to come to this course or be fired or.
No, I don't want to come.
Yeah, I hope not.
I lost.
Yeah. This is. I hope you choose your job and not this course. Okay. So what if we have more than 2 samples? Obviously, something we could do is, we say we have 3 samples. We could compare sample 1 with sample 2, 1 with 3, and 3 with 2. The way we've done it up to now. But there's another way of doing it. You could say a more frugal way, especially if you have more than 3 samples, which is called ANOVA. And ANOVA stands for Analysis of Variance. Okay, so we have here an example paper, and we want to look at tensile strength as a function of the concentration of hardwood in this paper. And you see that we have this concentration at 4 levels, and per level we do 6 measurements. Okay, and then we look and try to see, based on these measurements, if there's an effect of this factor, which is hardwood concentration. So we're slowly moving in the direction of design of experiments by doing this ANOVA. So we have a factor at 4 levels, and these levels we call treatments, and 6 observations, this we call the replicates. Okay? So we just had a discussion with one of the groups, how many levels you should have for your factorial experiment. 2 is enough. Okay, we have 4 here, but for your full factorial experiment, 2 to 4 is okay. So you have 16 treatments in that case, all right? And 2 replicates is enough as well. I don't want you to do too many tests. Let's be frugal also with your time. So 32 experiments would be okay. And remember, what's happening? You have to eat something. Okay. Yeah, please go eat. Health comes first, always. Right. Okay. So yes, yeah. We also did we also lose somebody else? The arsenic person is arsenic person is gone as well. Wow. Say that again.
She's back in the lab to take out the samples.
Oh, okay. She's measuring more arsenic. All right. So yes, getting slightly off track here. So I want you to still remember that these 32 measurements, you don't use that to do your probability plots. Okay, I've explained this already. So put this also on your page with tips. So do 1 experimental setting, so 1 treatment, if you like, so 1 experimental condition where you fix the 4 factors. Do that 15 or 20 times, and then look at the normal probability, log normal, Weibull probability, see if that works. Okay? Because if you do that on the full factorial data set, that doesn't make sense because you expect differences. So they should be different populations. Okay? So it's nonsensical to do that on your full factorial data set. If you don't understand it now, hopefully you'll understand it once you're studying the course. Okay, and remember, we want to do the runs in random order. Also here, they're done in random order because there may be some influence of temperature, other factors which we don't take into account as we're doing the measurements. So not to have this effect of one of the factors which we haven't controlled and which is going in a certain direction during our experiments, to have that make as some type of disturbance in our observations. We do this in random order. So if we look at our data set, this is the box plots. You remember that? And this is what it looks like for just plotting the 4 averages and the variance on this. Okay, so, and the way we look at this now is that they're all some average, overall average. This is the mu overall average, and there's a displacement from this average which we call this tau. So this is tau 1 for our first data set, tau 2, tau 3, and tau 4. And so this gives us, the sum of these two gives us mu 1, mu 2, mu 2, mu 3, and mu 4. All right. So a more general way of putting it, we have A treatments and observations. And for each of these treatments, we can then make a total, which we indicate like this. And the average of these observations we indicate like this. Okay? We also have the overall total. So if we total all the totals of these rows, we then get an overall total, and this is our overall average of the data set. Okay, so you see the notation how that is done. It's indicated once again here how that works. Okay, so this is this average mu, or the sum rather, of this line for treatment I, and this is the average for treatment I, and this is the overall total. As you can see, these are the data, each of the data points summed over treatments and replicates, and then we can have this big N, which is the total number of observations, and we can use that to calculate the overall average of our data set. So how does this ANOVA work? We take that each of our observations is the overall average, mu, plus some deviation of that, which is due to the treatment, tau. Okay, so if there is an effect of the treatment, this would be different from 0. And then some type of random deviation, which is, or error, if you like, which is this epsilon ij. Okay? So we look at each observation as consisting of 3 components: the overall average, some deviation because of the treatment, and some error because of measurement errors, and so on and so forth. All right? And of course we go, I goes over the number of treatments, goes over treatments, J goes over the replicas. So what is our null hypothesis is that all of these tau values, so the treatments have no effect. The tau values are equal to 0. That's the null hypothesis. And the alternative hypothesis is that at least one of them is different from 0. All right? So, how do we now see if we can reject or fail to reject this null hypothesis? So what we do is we look at the total sum of squares. This is SST, sum of squares total, which is the observation minus the overall average squared and summed over the replicates and the treatments. And this sum of squares, total sum of squares, consists of two parts. One which is due to the difference between the average of a treatment minus the overall average, and then the difference between the observation and the average of that treatment. Okay? So this is like an error term, okay? Because if we would have no errors, the I observations would all be equal to the average, right? And this refers to the treatment differences. So if we have the average and its difference, the average for a certain treatment, and it has a difference compared to the overall average, this then refers to these tau values. All right, so to summarize, we can divide this total sum of squares into a sum of squares of treatments and a sum of squares of the errors. So SS treatments is the treatment sum of squares, and SSE is the error sum of squares. All right, so how do we then do the hypothesis testing? We divide the sum of squares of treatments through the degrees of freedom for the treatments. We have A treatments, so that becomes an A minus 1. And for the sum of squares of the errors, we divide through A n minus 1. Because we have n minus 1 as degrees of freedom for one treatment, and we have A treatments, so we have to then multiply by A. And this gives the degrees of freedom for the errors. Alright? So our expected value for the mean square of treatments is equal to the sigma squared. So this is the sigma squared of the population. So basically the assumption that we make is that the variances for each of these treatments, the sample that we take for each of the treatments, the variances are the same. So this is the sigma squared. And for this expected value for this mean square of treatments, we have sigma squared plus a term which includes these treatments differences. So differences we have because of the treatment. So tau I squared summed over the treatments times n divided by A minus 1. The expected value for the mean square of the errors is the sigma squared. So basically what we're saying is that if we would have a situation where the treatment doesn't matter, treatment doesn't have an effect, we would basically just have one population. And this one population, we can estimate the variance of that population by looking at SS treatments divided by A minus 1. SS treatments being the sum of square of treatments divided by its degrees of freedom. Okay, this is the way we always do our estimates of the variance. And we can also do the same estimate of the variance through the errors. So that's the sum of squares of errors divided by degrees of freedom we have for this sum of square errors. And if our null hypothesis is true, all taus are equal to 0. This should be the same variance. And so we can then do an f-test on these variances. Right? And you see the logic in the reasoning. And so with our null hypothesis, we assume that the taus all are equal to 0. So that means this would be equal to 0, so that drops out. And so we can estimate the sigma squared through MS treatments, and we can estimate the sigma squared to the MS error, mean square error. And so we can then look at our test statistic as the ratio of MS treatments over MS error, and compare with critical values, boundary values we have for the F distribution. In this case, as we're looking for an effect of treatments, we are normally expecting that this will be larger than that. Okay? And so we look typically at an F value which is bigger than this F alpha. Although you could think this is a two-sided alternative hypothesis. We don't divide alpha by 2 here because obviously if we have an influence of treatments, this MS treatments should be bigger than the MS error. Okay? So it doesn't make sense. Claim that you have an effect of treatments if the variance which you calculate through the treatments is smaller than the variance that we calculate through the error. That's why we take alpha here. Is that clear or is that not so clear? Okay. So let's maybe go back a step. So if this is a situation here, right, you have a difference between the treatments. If you do the MS treatments, you would have a population which has values here, there, right? So that would be a fairly broad population, a fairly broad distribution. Okay? The sigma squared which we calculate through the errors is now this one. Okay? It's for each of the treatments separate. That's our mean square error. Okay? So that would be much smaller than the broad one which we have with the treatments. So if we have an effect of treatments, that pulls our distribution apart, and so we would then expect an estimate of the sigma through the treatments which is wider, broader, larger than the MS for the errors. Okay? So if you would find in your calculation that this is smaller than that, then it's nonsensical to do the calculation, basically. Because there's no indication in your data set that there is an effect of treatments. So that's why we take the full alpha here. Okay, because the other boundary wouldn't make any sense because that would be the boundary for this being smaller than that. So that doesn't make any sense. Okay. So yes, we can use the calculation shortcuts to do the SS total and SS treatments, and then we can calculate, because of the fact that total is treatments plus error, we can calculate the SS error through this equation here. So, say we have a data set, then we can make a table like this. Source of variation, treatments, error, total. We calculate SS total, we calculate SS treatments. The difference between these two is SS error. We know the degrees of freedom. From that we can calculate the mean square, treatments and error, and we make the ratio, which is our F statistic, and we do the point estimate of this F statistic. Okay? So our 7-step procedure then is looking at the taus, the difference between the strength of the paper for the treatments compared to the overall average null hypothesis. They're all equal to 0. Alternative hypothesis, at least one is different from 0. Our test statistic is MS treatments over MS error. We look at P less than 0.05, then we can reject the null hypothesis, and so we do the calculation of the total sum of squares, which in this case for our example would be 512.96. SS treatments, we did the calculation. This gives us 382.79. This is larger than, is it larger? No, it's not larger, it's smaller of course, because this is the total sum of squares. This is the sum of squares of treatments. So the difference between these two gives us a sum of square error. And this one we expect to be smaller than that one. Okay, that's what we were saying earlier. And the question is, how much is the ratio? And is this ratio significantly different from 1 so that we can reject the null hypothesis? And so we see when we do that, we know that the computed value of this is a good. Okay. This all right. So how do we get this value now? F0 is equal to 19.61.
We have to calculate the mean square first and then divide.
Exactly, we still have to do the mean square. So we can't just do the ratio of these two. So what I was saying earlier was crazy, of course. So we have to first divide through what here? We have 4 treatments. So we should divide through, this was our example here. We have 4 treatments. So we have to divide by A minus 1. Right? So this is divide this by 3. This SS error is 130.17. We have to divide by A times n minus 1. So this is 4 times, what was n? 6. So we have to divide by 20. And then that should give 19.61. Is that right?
Why by 20?
Why by 20? Did I make a mistake?
No, I'm just asking. No.
Okay, you're asking. Because we have to divide by A n minus 1. So A is 4, and if I remember correctly, n is 6. So A times 4 times 5 is 20. Okay? So does that work out? Did we calculate it? Who is good at this? Is there still somebody who has the energy to... It could... Hopefully this is correct. We have it here, actually. So 320. So it gives us 27.6, 6.51. That ratio is 19.61. Hopefully that's correct. assume it is. The total is given here. This is 22 degrees of freedom, which is a times n minus 1. Okay, so 4 times 6 minus 1 is the total. 19.6, not 6.1. Okay, yep, so it's been confirmed here. And so that p-value, let's see, the p-value is reported as 0.0, so it's very close to 0, because this is a very large value. So if we have alpha 0.05, what would be the limiting value? We have to look at f, for instance, 0.01, so that would be alpha 0.01, 320, and degrees of freedom of the numerator is 3, denominator is 20, we just said. So that's 4.94, which is still much smaller than 19.61. So we're much lower than this. Okay, so the p-value is really low. You see 10 minus 3.59, 10 minus 6. So we have a very strong conclusion that treatments have an influence. Okay, so we can say yes, there is. We can reject the null hypothesis. At least one of these taus is different from 0. Okay, and this is the table. So now we can look at how that works. So the sigma estimate that we have is the mean square error. Square root of that divided by n. This is an estimate of the standard deviation of the sampling distribution. Okay, so this gives us the width of the distribution around our estimate of the average for treatment. Okay, so this would then, if we look at this distribution and we would put this at 2, you would see it's difficult to distinguish between 2 and 3. And it's clear that there seems to be a difference between 1 being lower than 2 and 3, and 4 being bigger than 2 and 3. Okay, so that is in our conclusion. All right. We can look at residuals. So residuals is the difference between the overall average. Is that right, the overall average, or is it the treatment average? Let's see. Residuals. This is 10. So it's a difference. We're looking at the errors in the data. So we're looking at the difference between the measurement and the average for treatment. Okay, so this is -3, -2, and so on. And 0 at the end. And so if we plot the residuals, they should be normally distributed. That gives us an indication that we have been doing things according to the rules, that yes, this is one variance we can use for the complete data set. So the variance we find in each of the data sets is more or less the same. If we would find something which is not normally distributed here, we have to consider that our ANOVA method may not be appropriate for this data set. We can also look at residuals for the factors. So also here we get some indication of the variance for each of the treatments. And so the variances are not extremely different. So it's okay to assume the same variance. All right, so this is checking our assumption that we can use the same variance for all the treatments. Okay. So this ANOVA method is like a two-step method. First we see if there is an effective treatment, and then we go and look which treatments are different. As opposed to doing, if you have four of these, you would have to do all possible combinations, 1, 2, 1, 3, 1, 4, and so on, with the t-test for 2 samples, and that becomes a bit awkward. All right. So there is an additional possibility for this type of comparison, which is called a blocked experiment or a block experiment, where we do a block design. So say that, for instance, we're doing these experiments, and we've been using a machine for a number of days, and we're not sure if the machine is operational in exactly the same way each of these days. We can then try to see if there is an effect of the day on which we've done the experiment. And that would be, a block would then be a day. So, for instance, another example given here, we have our 2 different methods to measure shear strength. We now have 4 girders as the experimental unit, and so we could block the girders, the beams, and say, okay, we have our now 3 treatment methods as opposed to 2. 3 different methods. And we have 4 girders. So remember our paired t-test, we had just 2 methods, and we had maybe like 6 girders. So now we have a more general case, 3 methods, 4 girders. So we can then block, so it's kind of the generalization of a paired t-test. We block now the girders, so we put them in separate blocks. So we then have A treatments and B blocks, and we calculate the averages for the treatments and the averages for the blocks. And we now consider each of the measurement values to consist of the overall average, an effect due to the treatment, an effect due to the block, and an error. Okay? And so, once again, we can look at our total sum of squares, and now divide this in something which is due to the treatment, effect of treatment, effect of the block, and this is now the error. Okay? So we have now a 3-way split of our total sum of squares. And so this is, as you can see, the same information. Total sum of squares is SS treatment, SS blocks, SS error, and these are the equations which specify which is which. And so we can look at the MS treatments by dividing SS treatments with the degrees of freedom for the treatments. Same thing for the blocks, and the same thing for the error. And now we can do our F-test on the ratio of MS treatments over ms error and ms blocks over ms error. And so we can now see if there is an influence of the treatments, but also an influence of the blocks. Okay? And this is what we do here in this table. We have the mean square for the treatments, mean square for the blocks, the mean square for the error, and then we do the f-test on the treatments, but we can also do the f-test on the blocks. See if there's an effect of blocks. Okay, if we'd be interested in it. Alright, so let's look at an example here. We have 4 different chemicals, and we are looking at the strength of a fabric. They're used as part of the permanent press finishing process. 5 fabric samples are being selected, and we do a randomized complete block design because we have different types of fabric. That's 1, 2, 3, 4, and 5, and we have 4 chemical types. And so we calculate the averages for the treatment, the averages for the blocks. We can then calculate the total sum of squares, the treatment sum of squares, the block sum of squares. Sum of square error is then the difference between total sum of squares minus sum of square blocks, sum of square treatments. Okay? And then we can go from the sum of squares to the mean square. And we have to, in the case of chemical types, we had 4, so the degrees of freedom is 3. Fabric samples, we had 5, so the degrees of freedom is 4. The error, in this case, is what degrees of freedom? You can say totally we had 19 degrees of freedom, so the remaining degrees of freedom go to the error. If you want to have the formula, it's a minus 1, b minus 1. Does that work out? That should be 3 times 4, that's 12. That works out. And so this is the mean square for treatments, blocks, error. We make the ratio of 6 to 0.08. We get 75, which is a very small p-value. If we would do the one for the fabric, we would also get a big p-value. So we also get a big f-value, so we should also be getting a small p-value. So there's both an effective chemical and blocks. And so that helps us to distinguish the fact that we had different fabric samples and different chemicals, and get some type of statement on both of these. All right? And so once again, we can then look at our standard deviation on the sampling distribution. And this gives us the idea that 1, 2, and 3 may not be so very different. Obviously, 4 is very different. Okay? We can test again to see if we have a normal distribution of the residuals. This all looks fine. Okay? So this, hopefully, we finished on, yes, we did finish on time. At least that was successful. So we'll do a little poll to see if we like evenings or mornings. Yes?
Is it possible to put also a choice between a couple of evenings?
Oh, okay. So the poll would be the Friday morning.
Or maybe a choice
We can only do Friday morning because that's the only thing that's available in the morning. And we can do like Monday and Thursday evening. Is that okay?
Is Friday evening available?
Friday evening.
No. No, okay.